Good morning, everybody. We have been looking at applications of integrals, and mostly everything so far has been areas and volumes, right? But we know that integrals can be used for any type of accumulation. So if you remember, we looked at that Desmos that had all those open-ended questions, and any type of rate where we're looking for accumulation, we can use an integral. So there was my favorite banana problem where they give you the rate at which bananas are going off of a conveyor belt. And if we know how long, if we know the time period, we can do an integral to get the accumulation or the net effect. So we're going to do a couple examples like that, but these ones are more specifically related to science. So my science heads and my physics heads, you will like this section. Okay, so what we're going to talk about today is the concept of work. And in physics, work has a very specific definition. When we talk about work being done in physics, what we are talking about is some force causing a displacement on an object. Okay, so force and displacement are the two key ideas behind work. Okay? When a force acts on a body and displaces it. Now remember, displacement is the net effect, right? So if I go around in a circle, there was no displacement, and that's key. Okay? When a force displaces a body, we say that there was work done on the body. So work done by that force. And of course, all kinds of forces can do work on all kinds of bodies, right? If I take my fancy pen here, and I'm just holding it in the air, and I let it go, which I'm not going to do, it's going to fall, right? There was a displacement. The force that caused that displacement was gravity. Right? So if I drop my pen, gravity is going to do work on this pen. Now, pen's on the ground and I pick it up, I'm the one doing the work on the pen. But when I drop it, gravity's doing work on the pen. Okay. The amount of work that gets done literally only depends on two things: how much force was put on it and how much it got displaced. And it's a direct variation on both. The more work, or I'm sorry, the more force, the more work; the more displacement, the more work. It's a pretty straightforward relationship. Okay, so because it's a pretty straightforward relationship, it's got a pretty straightforward equation. Okay, and the amount of work done on an object is always going to be the force done multiplied by the displacement. Period, end of story. Okay, and like I said before, if there isn't any work, if there isn't any force on the object, there can't be any work done. And if there's no displacement, there cannot be any work done. If either of these quantities is zero, the work is going to be zero. Okay. Now, as far as units for work, the displacement is going to be a distance unit, and force is going to be a force unit, which is a Newton in physics generally when we use the MKS system. So the unit of force is a Newton times a meter, and it is absolutely acceptable to write, I'm sorry, the units of work. It's absolutely acceptable to write NM, like Newton meter. That's perfectly fine. Physics defines a Newton meter as a joule. So if you want to write a capital J for joule, that's okay too. AP will recognize both, but you don't have to memorize a new unit. If you're not already familiar with the joule, you can write NM, and we understand what it means. If the problem is in FPS, if it's in the hour system, then the unit is feet pounds, right? And I find it interesting that they kind of write it backwards, right? The pound is the unit force, and the foot is the displacement force, but they call it a foot pound. Guess that sounds better than pound foot. I don't know. All right, so the easiest questions we can see for work is where they give us a force, they give us a displacement, there's not really much to be done, right? So they say how much work is done lifting a 20 Newton box up 30 meters. Okay, so I have a displacement of 30 meters and I have a force of 20 newtons. Here we go. Would help if I wrote the equation right. Work equals force times displacement. So the amount of work is just going to be 20 newtons times 30 meters, or 600 Newton meter. Oh my goodness, Newton meters, or 600 joules. However you choose to write it. Okay. Now, obviously, this is not a calculus question, right? This is like a 8th grade science question if they introduce you to the idea of work. Now, you could see this on the AP as like a part A, right? But what we're mostly going to see on the AP is situations where the force isn't constant. Okay? If you have a constant force, then the work is steadily accumulating as you push at this constant rate, this displacement. Right? The calculus comes in when the force is no longer constant, right? The big example, and we'll talk about this later today, is like a spring. Right? If you go to stretch a spring, it might be real easy to stretch in the beginning. There's not a whole lot of resistance, right? But the further you stretch, the harder it becomes to stretch it because you're getting more and more and more resistance. So the spring is a really common example of a variable force, a force that is constantly changing. As the displacement changes, so does the force. Okay. When that's happening, we need calculus to calculate the work, because what we're going to have to do is use teeny tiny intervals, right? Since the displacement is since the force is constantly changing, we're going to have to say, okay, well, how much work was done on this teeny tiny interval from when the displacement was 0 to 0.1? Right? So we're going to use those teeny tiny intervals, and what are we going to do? We're going to make our intervals approach 0. That will give us our net work. Okay? Anytime we have a varying force, we use small intervals, or intervals, where are my words? And then we're going to make them approach 0 so that we can do an integral. Okay, so let's see here. Here's an example of a problem like this. It says the force required to move an object varies with its displacement. So in this case, here's our, instead of giving us a numerical number for force, we have an expression. So the larger x gets, the bigger the force is. When x is 0, the force is only 1 Newton. When x is 2, my force is going to be 9 newtons. And the more x grows, the bigger the force gets. Okay. So it says how much force, oh my gosh, how much work is required to move this object from a position of 0 to a position of 10. Okay, so here's what we know. When x is equal to 0, the force is only 1 little newton. By the time it gets to 10, it's 201. And in between 10 and 1, it's a constant change. This is a quadratic equation. It's a nice smooth curve, right? So between 0 and 10, this force is increasing. It's going to go through every value between 1 and 201. So it's not like I can just use an average or something and say, oh, well, we'll just use the average force over. No. We can, however, still figure out the work done. Okay? Because remember, work is force times displacement. Now, what I'm going to do is I'm going to calculate a teeny tiny piece of work. Okay. So in other words, an infinitely small amount of work would be that force, whatever it is over that interval, times the teeny tiny displacement. See the integral? Infinitely small displacement produces an infinitely small amount of work. So if I want all of the work, I can just integrate both sides. So work will be the integral of the force, which in this case is 2x squared plus 1, times the tiny displacement, or dx. And then our limits of integration come from our displacement. So remember, this integral is written in terms of x, which represents displacement. So our limits will be these values of x. So from a displacement of 0 to a displacement of 10. Okay. Anytime the force is variable, this is going to be how we get at it. We're going to start with our work formula. tiny, tiny displacement produces a tiny, tiny amount of work, and then integrate to get all the work. This is accounting for the fact that the force is constantly changing. Just like in the accumulation problems, we use the function to represent the fact that the rate was constantly changing. Okay. Now again, kind of if we go in order of how complicated problems are, the nicest thing is when the force is constant. The next nicest thing is when, even though the force is variable, they just hand us a formula for the force, right? They're like, there is this variable force, and here's the equation for it. We like that. I don't want to say the worst thing that can happen, because it's still not that bad, is that it is a spring problem, and they don't give us the formula for force. We're expected to come up with it. Okay, now, the way we come up with it is by applying something called Hooke's law. And again, you don't have to be a physicist for this. If you're in physics, you probably already know what Hooke's law is. Maybe. Okay, so Hooke's law is specifically about the work done when we are stretching or compressing a spring. Okay. And all springs are different, right? So Hooke's law talks about something called a spring constant. And the spring constant varies based on how stiff the spring is, right? So if you ever had a slinky, right, it's kind of like a very loosey-goosey spring. That's going to have a very low spring constant. And if you've ever experienced a garage door spring, which if you haven't, they're a real joy. They're so heavy, and garage doors are really heavy, right? But those springs that pull the garage door up and down, my gosh, you couldn't stretch one of those with your hands. Oh, maybe you could. Maybe you're very strong. But they're really, really heavy, and they're really, really stiff, right? Because when the garage door is down, they're all stretched out. And the way the garage door gets lifted is from that spring wanting to go back to its natural length. So when we talk about Hooke's law and the force that's required to stretch a spring, it's going to depend on that spring constant, right? How stiff is the spring? It's going to take a lot more force to stretch a garage door spring than it is to stretch a slinky, right? But also on how far we want to stretch the spring. If we only want to stretch a little bit, it's not going to take a lot of force. If we want to stretch it really far, it's going to take a lot of force. Okay? The other thing it depends on is how far the string is already stretched, or the spring is already stretched. So for example, taking our garage door spring example, if it's at its natural length and I only want to stretch it, say, 1 centimeter, if I grab one end and you grab the other end, we might be able to like pull it out 1 centimeter, right? So if going from a length of a displacement of 0 to a displacement of 1 might not be too bad. But if that spring is already stretched, say like 50 centimeters, and we want to go from 50 to 51, that's going to be harder to do. Is it's already stretched 50. So if you want to stretch it even more, it's going to be even more force. So the force is also depending on not just how stiff the spring is and how much you want to displace it, but where, if you will, that displacement is. If it's displacing it from its natural length, it's going to be less force than if it's already stretched and you're attempting to stretch it further. So when we're talking about springs, those are kind of the three things that come into it. All right, so Hooke's law is going to be what helps us get a formula for the force in a spring situation so that we can then take that into our work formula. All right, here's Hooke's law. Looks a little bit familiar, doesn't it? Looks a lot like the work formula. Okay. So in Hooke's law, this is the force. Okay. It's the force used or required, whatever you want to say, to stretch or compress a spring. Right? So it's really, it's just a difference here, not in quantity, but in sign, right? If I'm compressing the spring, that's going to be a negative displacement. If I'm stretching it, that's going to be a positive displacement. But the force would be the same either way, if the displacement is the same. And that's going to be in newtons, obviously. Right. This X is the amount the spring is stretched or compressed. Again, positive displacement versus negative displacement, stretched versus compressed. And then this little k right here is our spring constant or our force constant. Okay. The higher that value, the stiffer the spring. Now, we're not going to be approximating those or anything. What they're going to do is they're going to give us either going to hand us the spring constant, or they're going to make us find it. Which, as you can see, isn't too bad because it's a pretty easy equation. If they give us a force and displacement pair, we can figure out what K must have been. Right? For example, if they say I stretched a spring 20 meters and it took me 100 newtons of force, we can put the 100 and the 20 in here and conclude that K must be 5. Right? And if K is 5 for a spring in that situation, K is 5 for the spring overall. K is a constant that applies to an individual spring. So if they give you a pair of values, you can figure out what K is. But you do have to know this relationship to do it. Okay, so if we want to do work on a variable force, here's my tiny piece of work, here's my tiny displacement, and there's my force. So all we're going to have to do with our integral, like we did in that previous question, is integrate over the displacement that we're interested in. Now again, this might not always go from 0 like the problem we did. If we're stretching a spring from a length of 4 to 10, this would be 4 to 10. So it's not necessarily starting at 0. 0 would be the natural length of the spring. The displacement is the amount that it is stretched or the amount that it is compressed. This is your general formula for work. For springs, we're going to replace this F with a Kx. Okay, so here we go. We've got this spring. And it says it takes 10 newtons to stretch that spring 2 meters beyond its natural length. So I'm going to draw a spring. And I'm going to call it, this is good, I'm going to say this is its natural length. So if the spring's just laying on the ground, this is what it's going to look like. If I take that spring and I stretch it, what did it say, 2 meters? Okay. If I stretch it 2 meters, what they're telling us is that this 2 meters took 10 newtons of force. So to take this spring from whatever its natural length was out further to 2 more meters, it took me 10 newtons of force. I know that force has to equal the spring constant times x. So I can use this information to find K. So if 10 newtons was 2 meters, then I know that for this spring, the K was 5. In other words, for this spring, the force equation is 5x, because for a spring, the force is always Kx. Again, they could say the spring has a constant of 5, or they could do something like this. Either way. All right. So now that we know the equation for force, finding work won't be too bad. It says how much work is done stretching the same spring. See how they had to stress that it's the same spring so that we know that this 5 that we found can still apply. 4 meters from its natural length. Okay, so I now know that this force constant is 5, but now they're saying, okay, instead of only stretching it 2, stretch it 4 past its natural length. So here's natural length. Now we want to go out 4 meters, and the force, we don't know how much force, right, numerically, but we know we have an equation. And we want to know what work was done. So let's get it. If I want the work, I have to integrate force times tiny, tiny displacement. So in this case, my force is 5x, tiny, tiny displacement. And then I'm going from natural length, so a stretch of 0, out to 4. So for a stretch of 4. Okay. Remember that these numbers on the limit of integration are referring to the amount of stretch, not the length that it is. So for example, if they said that the spring has a natural length of 6 and we're going to stretch it to 10, we wouldn't integrate our x value is still going to be the amount of displacement from natural length, so we would still be integrating from 0 to 4. if you integrated from 6 to 10, you would be integrating, the number you would be getting would be a stretch of 6 to a stretch of 10. So just make sure that you pay attention to that, because sometimes they give you from the stretch from its natural length, and sometimes the way we see it is like they give us this and then they say how much does it take to stretch it 2 additional meters. In other words, you're not stretching it from its natural length, you're stretching it from the original stretch of 2. So our integral would be from 2 to 4. The x always represents the displacement, the amount you're stretching it. Okay, so again, that's Hooke's law. Long story short, we always know that work is the integral of force times displacement, and in Hooke's law, for springs specifically, force is always going to be equal to kx. Okay. So if they give you an equation for force, great. If they don't, it's probably a spring problem, and you're going to use kx, because that's really the only scenario that we learn how to write the equation for. Okay. Now, outside of Hooke's law, there are other situations where work is done, and they can get really creative with these situations. So again, what we're looking for is some force done over some displacement. Okay. So as soon as you see a problem, and this has lots of words in it, right? As soon as you see a problem with the word work, I'm looking for 2 things. I'm looking for a force and a displacement. That's what I know. So no matter how many words here and numbers they gave me, this problem, they want me to find the total work, is going to come down to a force times a displacement. We just have to figure out what the force was and over what displacement. Okay, so let's read this problem. All right. A leaky bucket. Calculus is famous for leaky buckets, right? It's got to be leaky, otherwise the force would be constant. Okay, so we have a leaky bucket that weighs 22 newtons empty, right? So I didn't give myself very much room here, but here's my bucket. That bucket, just the bucket itself, I'm going to call this W. No, I don't want to use W. I was going to use W for weight, but that's looking a lot like a W for work. We don't want to be confusing here. So let's just call it B for weight of the bucket. What do you say? Okay, so my bucket is 22 newtons. Okay. It's being lifted from the ground at a constant rate to a point 20 meters above the ground by a rope weighing 0.4 newtons per meter. Okay. I have to give my bucket a handle. And we're going to tie a rope to the bucket. Okay, so there's somebody up here. And they're pulling this rope up, right? They're hauling the bucket up. Maybe out of like a well or something, I don't know. And this distance is 20 meters. It says the bucket starts with 70 newtons of water, but it leaks at a constant rate. So in my bucket, there's some water. Here we go again. I'm going to call this H2O. And there's 70 newtons of water in that bucket. So I've got, what, 92 newtons in this bucket so far? And ironically, it leaks at a constant rate such that the instant it gets to the top, that's when the last drop of water drains out. And this poor calculus student did all that work for no reason. So, as you can see here, I've got 3 things going on. I got a bucket, I've got water in the bucket, and don't forget I have this rope here, and they gave us how much the rope weighs per meter. Now, why would that be? Let's think about this. The force that's happening here has to be counteracting the weight of that bucket, right? So we said we had 92 newtons down here, but it's actually more than that, right? Because right now there's 20 meters of rope, and that rope weighs 0.4 newtons per meter. So if I have 20 meters of rope times 0.4 newtons per meter, I have 8 newtons of rope hanging there. So in the beginning situation, in the very beginning, I've got 3,100 newtons of weight hanging there. Now think about what's going to happen as this calculus student starts pulling the rope up. Two things are happening. The more you pull up, the less rope is hanging, right? Because as he pulls the rope up, it's starting to kind of pile up on the ground here, right? It's no longer part of the hanging weight. You pulled it and it's kind of just flopping on the floor, right? So two things are happening. The further you pull, there's less and less and less weight from the rope, and there's less and less and less weight from the water because the water is also leaking out. So the amount of force that you need to pull that bucket up is constantly changing. In the beginning, you need 100 newtons of force. By the end, when you pull the bucket, that last little pull, there's not going to be any rope left hanging, and there's not going to be any water left hanging. So you're starting with a weight of 100 newtons, but as you pull and pull and pull and pull, by the time the bucket gets to the top, it's down to just the bucket, which is 22 newtons. But that weight is it's a constant change on the way up. So it's going to go from 100 to 22, and it's going to be a slow change on the way up. So if I can write an equation for how much my bucket weighs, that will be that variable force we need. It's 100 in the beginning, it slowly goes down to 22. So this force right here, the force we need, is going to be the weight of I was going to say bucket, but it's the weight of the bucket / rope / water. And here's my displacement. Right? We know that this has to come up 22 feet, so we're going to go from a displacement of none at all, it's on the ground, up to a full displacement of 20. Right? 20 meters? Yes. So all I have to do to get at this is figure out an equation for the weight of this bucket. Okay. All right. This force has 3 parts. Right? Bucket, rope, water. Let's do the bucket first. It's easy. The bucket weighs 22 newtons and it stays that way. Right? These two, not so much. All right, so let's talk about the water. Initially, I have 70 newtons of water. Right? So initially, I have 70. But slowly, 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 I'm losing water. But it says it's a constant rate, right? It says it leaks out at a constant rate, linear. So I can figure out the rate at which that water is leaking out because I know that it's gone by the time it gets up here, right? So I know that over 20 meters, I lost all 70 newtons of water. Okay? So to lose 70 newtons of water over 20 meters, that's 3.5 newtons for every meter that I pull the bucket up. So after 1 meter, I'm down to 66.5 newtons. After 2 meters, I'm down to 63 newtons, and so on and so on and so on, until at the top, at 20 meters, I no longer have any water in my bucket. Okay. So in terms of displacement, the amount of water in my bucket is going to be what I started with, take away 3.5 newtons for every meter, the meters being measured in x. Right? So at a displacement of 10, halfway up, I would have lost 35 newtons. I would have lost half my water. Right? By the time I get to 20, a displacement of 20, I've lost all 70. So 70 minus 70 would be 0. At a displacement of 0, I haven't lost any, so the water is 70 newtons still. Okay. Same thing is going to happen with my rope. I'm starting with a weight of 8 newtons. But the further up I pull it, I'm losing some of that weight. Well, here I don't even have to do a calculation. I know that every meter of rope I pull up, I'm losing 0.4 newtons of weight. They told us how much it weighs. I have to figure it out. So when I pull up 1 meter, I've lost 0.4. When I pulled up 2 meters, I've lost 0.8. When I pulled up 3 meters, I've lost 1.2. So I start with 8, and then as I pull up rope, I am losing 0.4 newtons every meter of displacement. Okay. So look at this equation for force. It's a little complicated, right? Because it's got 3 parts. It starts with the bucket, plus this rope, plus this water. So at the bottom, when x is 0, I'm going to have my 22, my 8, and my 70, or my 100. By the time I get to the top, this piece is going to be 0, this piece is going to be 0. All I'll be left with is my bucket. But in between, this equation is going to give me the weight at every single solitary displacement in between 0 at the bottom and 22 at the top. So my integral, didn't leave myself enough room. I'm going to go up here. The work here, we already said we knew it was going to be from 0 to 22. My force is 22 bucket plus 8 minus 0.4x rope plus 70 minus 3.5x. Now, we're going to simplify this. You probably want to, right? So you have 100 and then minus 3.9x. for your work. And again, this is a linear equation. We can integrate this. This could easily be a no calculator problem. Okay. So we see problems like this all the time with varying rates. I thought this one was interesting because it had the rope kind of into it as well. But we see leaky buckets all the time. They're a pretty common type of problem. Right. There's one more kind of problem, but I'm going to spare you for today, and we will talk about it on Thursday, and it is our friend, the conical tank. So I don't know if you remember the conical tank from before where we were filling a conical tank. We're going to do that again, except we're going to be pumping water out. And since we're pumping water out, there's going to have to be work that gets done. Oh, sorry, it's not water, it's olive oil. We're going to pump olive oil up and out of this tank. We will talk about this one in person. All right. For now, have a wonderful day, and I will see you soon. Oh, any questions? Put them in the end. See you soon.